Hello, my name is Rasmus and I'm a senior researcher and agronomist at the Department of Engineering at Aarhus University. I'll go to give you a talk about what we are doing within our little group called signal processing, but with special emphasis, or the major emphasis, on the agricultural domain. Let's see if I can get this up running. As I said, I'm an agronomist. I'm not an engineer. I normally start to state that because I'm between a lot of engineers, but as an agronomist I know quite a lot about the agricultural domain. But if I want something really done within signal processing, navigation, other things, I need to ally with engineers because their core competences is a lot deeper than mine. So we have a good synergy there. The group I'm within is working with signal processing with emphasis on image processing, analyzing it, and preparing it for creating the basis for manipulation. If you want to manipulate or act based on something you see, you need to understand the context. And that's where we are really putting in a lot of effort. If we look at who we are, and we are a department changing, people are coming in, people are coming out, people are getting new jobs. So I'm trying to say this is the present state of the group. And here are some of the core people. There's Henrik Karstoff, who's the leader of the group, Jakob Juhl. And here you can see Karstoff is the guy I'm really cooperating a lot with within imaging, pattern recognition. Then we have Jakob Juhl, that's geophysics, there's come back to that, audio. And then we have Henrik Pedersen. He's just left, but there will come a guy supplementing him, our group soon. Then we have Ole Gren. He's kind of linked to the commercial business. He is at a company called Agricultural Agri-Intelligence, and before that he was at Kongskilde Industries, and he is also my former colleague. I mentioned myself, and here is a lot of people. I'll come back to them. Some are from this university, some are partners who are studying at our place. Yeah, but let's dive in. This is our original poster for a group, and I'll take just briefly the other areas which I'll be working with within signal processing. There's the geophysical signal processing, and based on flying with a helicopter here and the magnetic resonance, you can realize the amount and the distribution of the water in the subground. It's not my core area, but it's related to agriculture because that's a valuable knowledge to have if you want to adapt agriculture to a more environmental friendly way of doing it. Then we have the medical imaging. That's really also a lot of number crunching, image acquisition, reconstruction, 3D and all that, and we have a lot of good synergy with this area. So now I'll dive a little more into the area I'm mainly playing within, BioSystems signal processing. And here we have, for example, the sound. If we see the birds, we have a problem with geese. They land and they eat all our crops and do other things we don't want, for example. And there, Kim Arild, who's an industrial postdoc at our department, he have a spin-off company, Wildlife Communication. And there they listen to the birds, and if they can hear and realize that this is some geese landing, they will say, okay, based on the way they sound, I know what dialect, and they will shout, this is the dangerous area. And normally the birds will then leave quite efficient. Then we have Gang 2. who has been working with Bies together with Peter Arndt, also one of the colleagues. And the interesting thing is that how do we count bees? And the idea we came up with was to look from the bottom up at the bees and then, yeah, start counting. I say, I just need to zoom in. And here you can see, and based on that and the pattern and behavior, they can gain information we can use to analyze how are the bees performing. Similar approach has been done by these two people within tracking pigs, weighing pigs, and I think there is a small video here from 2010 where they in fact just analyze where's the pig, how it's oriented, and then it identifies or track the patterns here. Another project that was a small spin-off project, we've been collaborating with Skywatch from Støvring in Denmark, and they are designing their own drone, very robust, simple to use. And then Tavs Nyert from one of my colleagues, he came and he's analyzing how efficient is different implements of injecting slurry into the ground, and that's quite hard to analyze. And then the brilliant idea emerged that what if we use hot slurry and we let this little one or a camera, thermal camera here, look at the ground. Then we developed an algorithm which could evaluate how much hot slurry can we see right after injection. That was just a funny little spin-off based on what we're doing. But let's dive into the core thing where I'm playing. We are going deeper and deeper. The vision here, for example, this is Fuse, but it's also John Deere and the other companies. The vision is that all the knowledge from the different equipment and the farm is available for the farmer in his tablet or phone or whatever. The problem today is, believe it or not, most of these machineries have sensors and everything, but they're not sharing it. They do nothing. They don't share it. And they see nothing in practice because they are not reacting using the information. The same as hearing, and they say nothing. So this nice picture is not real reality. It's a dream, and we have a big project working on that called future cropping, where we are trying to improve this. And there is a project with Kongskilde industry, Thomas Jensen, he's going to defend his PhD, where they try to put sensors in front, which can evaluate how is the soil in front of the implement and how is it afterwards. And when you can then, and you can realize that, then you can start to act and improve the performance of the implement. There's another nice little project with PhD student Jakob Pihl, who's also from Kongskilde Industries, and that's based on these small sensor balls. They can measure, for example, temperature and humidity. You put them into their grain stack and they monitor it, so you can avoid this. Let's zoom a little. This is because of humidity. The seed starts to germinate, and we don't want that. That's destroying what you've been harvesting. So if you monitor, here you monitor that's the temperature in the stack. There are several sensors, and over time that evolves. So something is happening. The temperature is rising, and if you have an alarm calling the farmer now saying he will go out and he will turn on the vents, and then you have solved the problem and you avoided this. So that's really interesting, and they are creating a lot of spin-off products there. Messages are popping in. Where you can do it in potatoes, seeds, A lot of different stuff. Yeah, the bees again. Another project, or this is several projects, this is the one where I'm coordinator, RoboWeedSupport. The idea is that we have an expert system up here, a brain, which know the brain or the expert system is saying, if you can tell me what is the population of weeds, which weeds, how big are they, the crop, then I can tell you what to put in your tank. If you just do that, they have proven you can save 40% in average in winter wheat. The problem is the farmer here, he doesn't have time to go into the field, the consultant doesn't have the time, the window is very narrow. So we are trying to make a bridge from here to the expert system and then back to the farmer. One thing is collect images, annotate it, and then give the farmer the advice based on the expert system we already have proven. We try to collect the images ourselves, go out and take the images with a smartphone, like this one, for example. That's hard, so we said, okay, can we do it with a drone?
And arm it. Then put in no throttle, then put out.
This is together with Danish Aviation Systems and a small other company called SenseFly, sorry. And here we just said, okay, can we take a cheap drone like the Iris, put a camera up below it, and then just fly out and land and take pictures. We got it to work, but you know, it's too sensitive for uneven ground. It works, and it's relatively fast. So now I don't have a video on that, but we are flying with a drone with an active sensor, the same drone, so it can go to descent, take a picture and continue. And we are also using a new Axiom drone from SenseFly, trying to use that one for that purpose. Because we need really high quality images. The weeds are like that. When we have received the images, consultants are annotating where are the weeds. That's a kind of idiotic job, but we need that to train on. Then University of Southern Denmark is looking over the shoulder, okay, he's saying this one is that weed, and that one is that weed, and there it is. So we are increasing the support for the farmer, the automation level. It's kind of the same as they're doing in Osnabrück. They call it remote farmer.1, 01 I think, together with the bunny rub. That's kind of the same loop. And when we have that, then Mads Dyrman from University of Southern Denmark, he will try to separate these, and he can do it with a very high he's very sure on what he's doing on the system for at least 16 different weeds now, and that's on controlled light conditions. So now we will look into what happens when we get it from the consultants, and we are going into that now. But in fact, this system, Plant Protection Online, doesn't need such a... It's okay if you recognize most of the weeds. You don't need to take all of them in order to get these 40%. Of course, when we fly, you saw the drone, we can also crash with the drone. So, yeah, just to show you that it's not that easy. Then there's also, for example, the grass seeds, you can't recognize them. It's too hard, very small, and even the expert has a hard time doing that. But if you do it in the green or the yellow crop, that's when it's just before harvest, then we can look at the green areas, that's grass and other weed patches, and then we can recognize this. That can solve that problem if we just memorize it. We also have other projects with drones. That's, for example, Anders Mortensen, who's at the Department of Ecology, but he's also sitting at our little group. He's doing image processing. And that's based on catch crops. Catch crop is when you harvest, then there's nothing to catch the nitrogen, then you seed, for example, fodder radish, and then that one will collect the nitrogen. Problem is, there's a high variation, so it would be nice to know that. So what he did was to take a drone, fly with it. Let's look at that one first. And there you see all these images is very high resolution. I can't show it better than this on this screen. But then he starts to analyze these images and recognize, okay, this is radish, this is spill grains from the combine. Put that together, and when he do that, then he get a map like this. It's not the final map, you can see there's still some artifacts here, but you get an idea of there's a high variation from no nitrogen to 70 kilos of nitrogen per hectare. That's a huge span if you look at the variation. You can see tracks here from heavy machinery. So you need to put that into consideration when you add fertilizer to the soil. Nobody is doing that at the moment. That's also image analysis. Then Anders is also working on using the Ebee and then a sensor with several waybands which are highly specialized. That's based on, you have, here's the reflections. This is it's funny they make this blue. It's the green area, this is the red area, and this is transition to the near infrared you can't see. You can compare that here, so we have the green and we have the red, that's what the plant is eating to get energy. And here it's protecting itself. This transition, you use that to evaluate what is the amount of nitrogen. For example, this sensor, and that's together with Animan, they're coming with some really interesting stuff from France and results in winter wheat soon. The problem with the current system you saw from, for example, combines, this map, for example, that's bullshit. This is bullshit. And why do I say that? You can see the spreader here. That one is spreading the seeds all over. You cannot control it with this precision. If you have a boom spreader like this, you can do it. But it needs a map. You cannot use a combine for that. The combine is also mixing it all up. We can see here example of a combine inside. You have all the grain, straw coming in here with grain. You trash it, it's mixed, all this process is mixing it all up. And that is a problem. I think we got the main idea here. I don't know why YouTube is not so supportive right now. But the good thing about the combine here is that you can weigh the amount of grains quite accurately, but it's a mixture of a huge area. Like you see here, it's a mix. But if you have this drone, this one can measure the amount of chlorophyll required per square meter, which is related to the yield. We mix the high resolution and all that stuff together. Then we can get a very precise map. We are looking at that in future cropping, and I know several other companies and research institutions are moving in that direction. We have seen that one. So, that was another little project. Then we have, if we are here, we have reduced the amount of herbicides with 40% without even, the farmer doesn't even have to buy a new sprayer. It's for free, because if we have a drone company collecting it, doing the analysis, he will of course pay that, but he will also save a lot of herbicide. Let's say we have that. Then we had another project called the Intelligent SprayerBoom, which has ended now. But the idea was, if we have cameras all over the boom, we analyze it on the go up to 12 k's per hour. Then what is crop and what is weed? That's a heavy one to do. But if we do that, then we can obtain savings, significant savings. What you see here is different amount of, just need to see, thresholds. When do you start to spray? So if you are here, you spray all the time. If you're here, you spray less. And what you save is illustrated. I think I need to, here. So here you don't use anything. It's a really high threshold. But you can see the weeds also growing. And this is different densities. But the conclusion here is, if you use this algorithm in maize, which is the easy one, then you can save up to between 70 and 95% of your herbicide. Of course, if you have a field which is full of weed, you cannot save that. But then you also have a need of using herbicides. The problem is that the camera technology was not ready. So we needed to use a robot, as you can see here. Let's see. So we had a sprayer, a robot where light was controlled, and then we drove with it. That's the compressor you can hear. So we drove with it, and you can see it's only spraying certain small patches. But we could do that and save a lot of herbicide. I don't know if that's nitrogen, just because we've just been talking about that. However, after the project, Amazon was a partner here. So, this year, in 2 weeks approximately, they will present AmaSpot, and that's the kind, it looks like a spin-off. We couldn't get the imaging up running, so they found some partners in Germany. And what they did was they placed these the whole way, so they can see the whole span of the boom. So you have a sensor looking down, detecting the crop. 60 centimeters after, they evoke a nozzle and they spray if it's green, and they can kill it. It's based off green sense, a sensor here. It's not vision. And then you have the nozzle, and you have a fan. Kind of the intelligent SprayerBoom, but here it's operational. The idea is that this sensor you have here, you have the nozzle here. Let's go a little closer. And then when it's moving, it's measuring again, very small area. Is it green? Yes or no? If it's green, we spray. So you cannot discriminate maize and weed. But again, you save a lot if there's no weed between the crops. But what we are working on is, so everything is up running except of the imaging part. We can do it, but it's too expensive. There's what called the edge sensor from Germany, but it's too expensive to put all over the full boom width. So we are in the future trying to solve that problem. So 40%, and in fact they have showed they can save in, I think it was between 60 and 70% they claim they can save with this technology. But if you have 40% here, 60 or 70, and we add that together, whoa, it's a lot we can save, or multiplied it will be. Then we have OptiMek. That's a mechanical weeding with a robot, or an implement. And what we looked into there is, if we have this robot, then we can start to, and it's moving our implement, then we can start to do mechanical weeding within the rows. But we can also look at the competitiveness of, if we make the row distance instead of that, like that, and then the crop will be a little further, but the pattern will be more competitive to weed. What effect does that have on yield and on weeds? But we have a project working on the navigation part too. This is a former project, and it's together with Peter Gorm, software engineering, Complex, that's industrial PhD I'm supervising together with Peter Gorm. So that's model-based software development. And here's an example of a project. it's really raining heavy that day. But it's running autonomously, it's cutting the grass, and it has also been doing that in lowland. It's working quite well, so that's a kind of proof of concept of the idea. But the problem is we need a sensor which can detect what is in front, so it's safe. And of course, if you recognize OptiMek, again, enough music. This one navigating and it's mechanical. That's what you can recognize here. So there's some work on making that autonomous. Several other companies, Bosch is looking into the area, for example, too. You can see it at Agritechnica this year. But also we use the drones that you've seen earlier. That showed up to be a real power tool. Here's a trial with 500 different parcels. And you see something went wrong sometimes. There's different road distances. There's big road distance here, there's less here. And different densities. So if I need to analyze this, it would be nice that I could pinpoint the bad parcels. And this showed to be a real good tool to do that. So when I analyze the yield and all that stuff, I can get rid of them. So here you can see that if they're seeded in sync or as an offset, like this, or I don't know if I can show that like this. So that's a close-up, and now I can start to analyze. There's something wrong here, there's something wrong here. I can exclude that from my analysis. So that showed to be a really valuable tool, combining the knowledge we already have. That was my daughter coming home. Then we have, as if you recall, I said we need to have safe equipment. So this is another project called Safe Farming from the Innovation Fund Denmark with several partners. So the idea is, can we make safe equipment? If we can make that safe and make the perception, then we can start to do something more intelligent, like I have said several times. For example, here, if the robot realizes there's something in front, two humans, then it can start to reason. Should I try to honk on them, say, get away? Should I stop? Should I go slow or should I go around it? It can start to reason about that. But you need the perception, and that's what we are playing with here. We also need to have an efficient way to do modeling and simulation, because if you go into the field, there's so many different parameters you can turn on. So you need the modeling and the simulation to detect the errors before you build it. It's a lot easier to do it in a simulated environment than the real environment. So here you can see, what if it's this is a mink feeder we are working on with a company. And here we started to simulate different solutions. How should we solve the problem for them? And there you can realize some misunderstanding between the software people, the designers, the engineers, and that caused a lot of stuff for us, or potential problems. Then it ended up with this solution. We have music again now. At least it's not engineering music, it's terrible often, I think. And now it's in fact driving in the mink, feeding the minks. We are still working on making it a little more robust with the perception, but the main architecture there. So next year I think there will be something ready for the farmers. And that's a PhD student. He is in fact not a PhD student more. He's working for me, and hopefully going into a postdoc together for Peter Gorm here. Then we have all the sensors we put here in order can we detect, for example, this little one. Let's go closer. Bambi. If we kill that one when we are cutting the grass here, that's not good for Bambi, it's not good for the person. It looks like this, for example. That's a nice one. The farmer doesn't have to go out and kill this one. It's dead. But sometimes it's not dead, it's just missing the legs, so he needs to kick it in the head or do something with whatever he has on the tractor, and that's not nice. If he doesn't find it and it's collected into the silage, then the cows can die of it. So there's several benefits if we can solve that. Then we have another project where we are trying to do another way of getting rid of Bambi. Bambi, or fawn, small fawn, you cannot smell it. And a dog cannot smell it, you cannot hear it, it's hiding like this. It's done that for centuries, thousands of years. It's efficient, except for after humans came with the machine. So what we're trying to do is, can we find it with a drone, a thermal camera? Here we are putting out artificial Bambis, and they look like this when we are going in 60 meters. So we have an idea if it works. When we identify where the fawn is, or Bambi, then we go out and urinate with, for example, Canadian bobcat, a predator. What happens is then in dawn, or in dusk, then the mother comes and it can smell there's predators here, and it calls on its fawn and it gets away from the field. We have been trying this year, but we didn't get everything up running. We have indication of that, at least we cannot say it doesn't work, but we are not entirely sure if it works. So here we have the thermal imaging, we have a height model, we have the orientation of the Ebee when it takes a picture, and then we can predict it. That's what we're working on here. And then we look on, are the fawns moving if we have been urinating the day before? Hopefully we can get that up running. But let's get back to not safety, but save this project. So if we have removed at least a lot of them, then we have less to detect on the implement. There is a project called VildtVenlig. They tried to do it in Germany and they didn't have really success. So this will be a help what I just showed you. But we are working on still trying to get it solved. And here you can see one way is to use thermal. It can see if people are hot. And RGB, that's your camera in your phone here. And then we just tried to take from the automotive industry because they're really putting a lot of effort in. Okay, I thought I had that in the link, but let's have a look. Nice music, so my choice. But here you can see a lot of small kits. We just took the classical open source algorithm detecting pedestrians, and it's doing quite a good job. Peter has improved it. It's not implemented here. We haven't added thermal imaging yet, but we are close of doing that. But it's just to show that your open source algorithms are quite good, even though they have not been trained in this environment. It's been trained in the urban environment, and it's doing quite well. Then we have an active sensor. I could say Kimaril here is working on, can I see bird nests based on RGB and other sensors? Because if you come with mechanical weeding, you're undercutting the soil. If there's a lot of bird nest, if it gets herbicide in the head, it's not too bad. It's not nice to get it, but it doesn't destroy the eggs. But if it's mechanical weeding, we need to detect the nest and then make the machine act. So lift up the implement, go over the nest, and then lower it again. Here you can see Mikkel. He's working on active sensors, so to say, radar and LiDAR. And I will focus on LiDAR here. So the Google car, you know, it's scanning with a lot of beams. We have one with 32, this is one with a lot more. And it can recognize all the way around there's objects sticking up. And here's a video of this is a raw feed from the LiDAR. And here you can see Mikkel has processed it. So you can see people finding a ground plane, trying to identify what is sticking up. So you can in fact see it's colored differently, what is sticking up. And he is working at the Center of Precision Ag in Australia at the moment, and they're doing some of the same. I'll come back to that later. But what if we mix these two? For example, stereo matching. Like me, I have two eyes, and by looking at the correspondence, then I can mix the two. But you need to have correspondence. A white wall is really hard to do something with. But here you can see there's perhaps a tractor here, there's two persons, but it's sparse, not good stereo matching. But if you mix it with the LiDAR support, then you get an improved matching, and this is just some rough results I'm showing here. So this is how we try to mix the different sensors in safe, trying to make safe equipment, try to recognize what is it human, is it a stone, so we can reason on what to do, and so also assist the farmer when he's sitting in the tractor, for example. Then there's a project here we didn't get, but we would really like to play with it. We have, milking robots is hot, but it's not so hot in Denmark anymore. And why not? One problem, if you say organic farmers, is that the cows, they must go into the field and get their own grass, at least in a large portion of the year. If they're doing that, they have to walk quite far, and they have to go back and get milked. With a milking robot, it can only take one cow, so it needs to milk all day. So it's not, you cannot go into the field and go back to get milk. So the idea was here that a colleague I had, Frank Ortson, he had a project to then move the milking robot into the field, and then the cows could get milk in the field. But the problem is cows forget that they need to get milk. And if now the milking robot is far from the farmer, so it's a hard job to get the cows. So the idea was to have tags on the cows. The milking robot realized there's a cow missing, and then a shepherd. So that's a robot is going out locating the cow and herding it into the milking robot. They have done some similar stuff in Australia. Let's have a look. Where Mikkel is currently.
The objective of this project was to operate an unmanned ground vehicle robot.
Of course, when you're exercising this, the net
amongst
is
the
not
herd of
optimal.
dairy cows. In this project, we investigate remote control herding and cow detection and tracking. We were able to remotely operate the UGV from the vantage point seen.
So they are remotely controlling this one, but here you can see what the LiDAR is realizing, and they can put that together and realize where are the cows and track them. So there's some technology coming there which can support the idea of having the milking robot in the field, so the cows can be organic, so you can have milking robots at organic farms. That's not really a good option at the moment. But to drive is very inefficient, so could we do it with drones? It's also more sexy, I think. And there's some people who have been playing with drones. Let's see, I'll just go forward. So they fly with a drone out. Can I find a cow? Some cattle I need to move. So now it's realizing, oh, there's a drone here. And in fact, you can move the cows with a flying vehicle like a drone. So if we can get that up going with perception and everything, then we have a way of doing it a little more efficient than having a vehicle on the ground. And that one can do other stuff. Of course, you also need the permission to do it like that, but you know, the future. Perhaps we will get that permission in the near future. And in fact, technology is coming, which has just been presented. Several from, I think it was Intel. Take the sound again. The idea is that you can have 3D cameras looking all the way around, and this drone is capable of navigating within a forest. That's quite impressive. But you can also use that for identifying cows and navigating. So the basis is there. This drone also have a huge potential, and we are looking into that one. So that was a project we would like to play with. Perhaps it can inspire other people to do it if we don't get the money. Another project which didn't get funded in the first run, which I believe is really nice for signal processing people and imaging people, engineers in general, is what if we can grow a crop totally artificially? We don't need to go out where it's raining, we don't have soil compaction and all that herbicide problem. We just close it totally. This is what people have been dreaming of, kind of vertical farming. But why not go to the extreme? That was our idea. Why not do it totally artificial? Artificial light, you just put water in, nutrients, whatever you need, you have robots, and then you just grow the crops. That would be a really nice project also for all people within signal processing. How is the plant performing? How do we harvest this? There's a lot of stuff you need to analyze, but it's in a more controlled environment. So this was an introduction to what projects I'm involved in, or group here, signal processing, especially with focus on the BioSystems signal processing within agriculture. I hope that will give you an idea of what we are doing. And yeah, I have to update it within half a year because new projects are coming, all that stuff. But feel free to comment and I'll see if I can answer them.